take a slow breath and allow the outside world to gently fade. For a long time, humanity believed it had a fairly clear story about how the universe began and how it grew. Galaxies were thought to appear slowly, stars were expected to take their time, and the early universe was imagined as a dark, chaotic place, gradually organizing itself over billions of years. That story felt steady, familiar, almost settled. Then, a new eye opened in space. Far beyond Earth's atmosphere, a telescope began observing the universe with unprecedented clarity, not by rushing, not by forcing answers, but by quietly collecting ancient light that had been traveling for billions of years. And in that light, something unexpected appeared. Galaxies that looked too large for their age. Stars shining where darkness should have ruled, structures forming earlier than any existing model had predicted. In this slow, unhurried journey, we'll explore how these observations are gently but profoundly reshaping our understanding of cosmic history, not through complex equations or urgent conclusions, but through careful reflection on what the universe is revealing when we simply take the time to look. This is not a story about mistakes or failure. It is a story about discovery, about realizing that the universe may have grown up faster, stranger, and more creatively than we ever imagined. Before we begin, take a moment to settle in, and if you enjoy slow, thoughtful journeys through the universe, consider subscribing. These long-form explorations are designed to be calm, unhurried, and endlessly fascinating. As we move forward, allow the scale of time and distance to soften your thoughts. Let each idea arrive quietly, without pressure to remember it. If your mind drifts, that's perfectly fine. If you fall asleep, the universe will continue unfolding without you. The light we are about to follow began its journey long before Earth existed, and now, at last, it is telling us a story we were never quite prepared to hear. For most of modern astronomy, the early universe was imagined as a slow, careful place. After the Big Bang, everything was supposed to take its time. Matter cooled gradually, gravity worked patiently, small clumps of gas formed first, then merged again and again, over hundreds of millions of years before becoming the first true galaxies. This picture felt reasonable because it matched both theory and the limits of what we could observe. The universe, in its youth, was expected to be simple, faint, and immature. That expectation shaped decades of scientific models. Astronomers built simulations that showed tiny galaxies forming first, slowly assembling into larger ones. Massive, well-organized galaxies were supposed to appear much later, after countless generations of stars lived and died. The early cosmos, according to this story, was a kind of cosmic infancy, awkward, dim, and unfinished. The James Webb Space Telescope did not set out to challenge that story. Its purpose was straightforward: look deeper into space, and therefore further back in time than any telescope before it. Because light takes time to travel, observing distant objects is the same as observing the past. Webb was designed to capture the faint infrared glow of the first stars and galaxies, whose light has been stretched and reddened by billions of years of cosmic expansion. What scientists expected to find were small, faint, chaotic objects, early attempts at galaxies still figuring out how to exist. What they actually found was something very different. Webb began detecting galaxies that were far brighter, far larger, and far more structured than predicted. Some appeared only a few 100 million years after the Big Bang, yet they already contained billions of stars. They had clear shapes, dense cores, and chemical signatures suggesting rapid star formation had already taken place. These were not cosmic infants. They looked more like fully grown systems that had somehow skipped childhood entirely. At first, researchers were cautious. Extraordinary claims require extraordinary scrutiny. Could these galaxies be closer than they appeared? Were the distances miscalculated? Was dust making them look brighter than they truly were? Every alternative explanation was tested, questioned, and rechecked. But as more data arrived, the pattern held again and again. Webb showed a universe that seemed to mature far faster than theory allowed. This created a quiet tension in cosmology. The laws of physics had not suddenly stopped working. Gravity still behaved as expected. Nuclear fusion still powered stars the same way it always had. And yet, the timeline no longer made sense. Something in the story of cosmic history was missing, or at least incomplete. One possibility is that the early universe was far more efficient at turning gas into stars than we believed. In modern galaxies, star formation is relatively slow and regulated. Gas clouds collapse, but feedback from stars, radiation, winds, supernovae, limits how quickly new stars can form. In the early universe, conditions may have been very different. Denser environments, fewer heavy elements, and more abundant raw material could have allowed stars to form at astonishing rates, building massive galaxies in a fraction of the expected time. Another possibility is that our understanding of dark matter's role in galaxy formation is incomplete. Dark matter does not emit light, but it provides the gravitational scaffolding on which galaxies grow. If dark matter clumped faster or more efficiently in the early universe than current models assume, it could have accelerated the formation of large structures. Webb's observations may be hinting that dark matter behaved differently in the universe's youth than it does today. There is also the question of the first stars themselves. Known as population 3 stars, these hypothetical objects were made almost entirely of hydrogen and helium, the simplest elements created after the Big Bang. They are thought to have been extremely massive, short-lived, and incredibly luminous. If such stars formed in large numbers very early on, they could have rapidly enriched their surroundings with heavier elements, allowing subsequent generations of stars and galaxies to form much faster than expected. James Webb cannot see population 3 stars directly, but it can detect the chemical fingerprints they would leave behind. Some of the galaxies Webb has observed show signs of surprisingly early chemical complexity, suggesting that intense stellar activity occurred much sooner than predicted. What makes this situation remarkable is not that scientists were wrong, but that the universe is revealing more nuance than our simplified models captured. Cosmology has always relied on a balance between observation and theory. When observations change, theory must adjust, not as a failure but as progress. This process is slow and careful. No single Webb image rewrites cosmic history on its own. Instead, each observation adds weight to a growing realization. The early universe was not a quiet, hesitant place. It was active, efficient, and surprisingly capable of building complexity almost immediately. There is a deeper implication here, one that goes beyond galaxies and stars. Time itself in the early universe may not have felt the way we intuitively imagine it. In a denser, hotter cosmos, processes that take billions of years today may have unfolded far more rapidly. The universe's first few 100 million years could have been a period of intense creativity, where structure emerged not slowly, but explosively, though still governed by the same fundamental laws. James Webb's discoveries do not erase the Big Bang, or overturn relativity, or invalidate decades of work. Instead, they reveal that the path from simplicity to complexity was not a straight, gentle slope. It may have been steeper, faster, and more dynamic than anyone expected. There is something humbling about this. Even with powerful telescopes and sophisticated equations, the universe continues to surprise us. Not with chaos, but with competence. It seems to have known how to build itself long before we understood how that building should work. As Webb continues its observations, this tension between expectation and reality will likely deepen. Some theories will be refined, others may be replaced. New ideas will emerge, not because the universe changed, but because our view of it finally sharpened. Cosmic history is not being rewritten in anger or confusion. It is being rewritten quietly, carefully, and with a sense of awe, as ancient light reveals that the universe, from its very beginning, may have been far more capable than we ever imagined. As the first shock of James Webb's discoveries settled, scientists began asking a deeper question. If the early universe produced massive, well-formed galaxies so quickly, what does that say about the timeline we thought governed everything? For a long time, cosmic history was imagined as a careful sequence of steps. First came darkness, then faint stars, then small galaxies, then, much later, the grand spirals and ellipticals we see around us today. This order felt logical because it mirrored gradual processes we observe in the modern universe. Slow growth felt natural, rapid maturity felt suspicious, but the universe James Webb is revealing does not seem suspicious, it seems confident. One of the most unsettling aspects of these observations is how common early massive galaxies appear to be. If Webb had found just one unusually large galaxy in the early universe, it could be dismissed as a rare outlier. Nature, after all, allows for exceptions, but Webb keeps finding them. Again and again, in different regions of the sky, at different distances, galaxies appear that look far too developed for their age. This consistency matters. It suggests that rapid galaxy formation was not a fluke. It may have been the norm. To understand why this is so disruptive, it helps to think about how astronomers reconstruct cosmic history. They do not observe the universe at one moment in time. Instead, they see a layered archive of light. Nearby galaxies show the universe as it is now. More distant galaxies show it as it was billions of years ago. By stitching these snapshots together, scientists build a timeline of cosmic evolution. James Webb has extended that timeline further back than ever before, and what it sees near the beginning does not line up smoothly with what comes later. The early universe, rather than starting small and simple, appears already complex, crowded, and productive. This raises a quiet but profound possibility. The universe may have crossed key thresholds much earlier than we assumed. Thresholds where gravity became dominant. Thresholds where gas cooled efficiently. Thresholds where stars ignited en masse. Once those thresholds were crossed, growth could accelerate dramatically. In other words, the universe may not have spent much time hesitating. There is also the question of efficiency. In modern galaxies, star formation is often inefficient. Large reservoirs of gas can sit quietly for long periods, forming stars only slowly. But in the early universe, conditions were extreme. Gas was denser, the background radiation was hotter, distances were smaller, gravity had less space to work across and more material to pull together. Under those conditions, the conversion of gas into stars may have been remarkably efficient. Entire galaxies could have assembled themselves in cosmic moments rather than cosmic ages. Webb's observations may be showing us the result of that efficiency. Galaxies that raced ahead while our models assumed a walk. Another layer of complexity involves feedback. In today's universe, stars and black holes regulate growth. As stars form, they heat and stir surrounding gas, slowing further star formation. As black holes grow, they can release enormous energy, preventing gas from cooling and collapsing. These feedback mechanisms act as brakes, keeping galaxies from growing too fast. But those brakes may not have been fully installed in the early universe. The first stars and black holes may not have been numerous or powerful enough yet to regulate growth effectively. Without strong feedback, galaxies could grow unchecked, rapidly converting gas into stars before the brakes finally engaged. James Webb may be showing us galaxies caught in that brief window, a time when growth outpaced regulation. There is also an uncomfortable implication for the age estimates of some objects. If galaxies appear more mature than expected, it raises questions about how we infer their ages. Astronomers rely on models that link a galaxy's brightness, color, and chemical composition to its history. If those models were calibrated using assumptions that no longer hold, the ages we assign may need refinement. This does not mean scientists have been careless. It means that models are only as good as the data available when they are built. James Webb is now providing data from a regime no one had access to before. And this is where rewriting cosmic history becomes necessary. Not in the sense of discarding everything we know, but in the sense of adjusting the story's pacing. The universe may have followed the same fundamental rules we understand today, but it may have played them much faster, much earlier. There is a poetic symmetry to this idea. Just as human history can accelerate during moments of intense change, cosmic history may have had its own periods of rapid transformation, moments when conditions aligned perfectly, allowing structure to blossom almost immediately. James Webb's findings also force scientists to revisit the meaning of early. In everyday language, early implies primitive. In cosmic terms, early may simply mean efficient. The universe did not need long preparation to begin building complexity. It may have been ready almost from the start. This realization shifts how we think about the nature of cosmic time. The first few 100 million years after the Big Bang may not have been a slow prelude, but a defining act, a time when the universe established patterns that would echo for billions of years afterward. And there is a quiet elegance in that. The same laws of physics that govern stars today may have been fully capable, even in the universe's infancy, of producing richness and order. Nothing special needed to be added, nothing exotic required. The universe simply began and immediately began building. James Webb is not shouting this revelation, it is whispering it, through faint infrared light captured from unimaginable distances. Light that left its source before Earth existed, light that travelled across expanding space untouched by memory, until it reached a telescope built by a species still learning its place in the cosmos. Each observation adds a sentence to a revised narrative, a narrative in which the universe is not a hesitant beginner, but a confident creator, not a slow learner, but a rapid experimenter. As scientists continue to analyze Webb's data, they are doing what science has always done best, adapting. Equations are being refined, simulations are being rerun, assumptions are being questioned, not out of doubt but out of respect for what the universe is showing. Cosmic history is not fragile, it does not shatter when new facts appear. It deepens, it gains texture, it becomes more honest. And perhaps that is the most important lesson James Webb is teaching us. The universe does not owe us a simple story, it owes us only reality. And reality, when observed closely enough, is often richer, faster, and more surprising than our expectations allow. The rewriting now underway is not an erasure of the past, it is a clarification, a reminder that the universe has always been capable of more than we imagined, even at the very beginning. As the implications of these discoveries continued to unfold, another layer of cosmic history began to feel less certain than before. The idea that the early universe was dominated by darkness and delay. For decades, astronomers spoke of a long cosmic dark age, a time after the Big Bang when the universe expanded and cooled, but before stars and galaxies truly took shape. It was imagined as a quiet, waiting period, empty, cold, and largely uneventful. James Webb is suggesting that this darkness may not have lasted as long as we once believed. Instead of a prolonged pause, the early universe now appears to have transitioned rapidly from simplicity to activity. Light seems to have returned sooner, structure seems to have emerged faster, and complexity appears to have gained momentum almost immediately after the first conditions allowed it. This challenges not just timelines but intuition. The idea of a slow beginning was comforting in a way. It suggested that complexity requires patience, that the universe needed billions of years to experiment before getting things right. But Webb's observations hint at something else, that once the basic ingredients were present, the universe wasted no time using them. This raises an uncomfortable question. If galaxies and stars formed so quickly, what does that say about the conditions immediately after the Big Bang? Were they more finely balanced than we assumed? Or did the universe possess an inherent tendency towards structure that our models have underestimated? One possibility is that small fluctuations in the early universe were amplified more aggressively than predicted. The Big Bang left behind tiny differences in density, slight variations in how matter was distributed. For years, simulations showed these differences growing slowly under gravity's influence, but Webb's findings suggest those fluctuations may have grown faster, collapsing into stars and galaxies with surprising efficiency. If true, this would imply that the universe was primed for structure from the very beginning. Not fragile, not tentative, but ready. There is also the role of cosmic expansion to consider. In the earliest epochs, space itself was expanding rapidly, but matter was also much closer together. Distances that feel enormous today were once comparatively small. Gravity did not need to reach as far. Gas clouds could collapse more easily. Interactions were frequent and intense. In such an environment, time behaves differently in a practical sense. Processes that feel slow today may have unfolded rapidly simply because everything was closer, denser, and hotter. The early universe may have been brief in duration, but rich in action. James Webb's observations invite us to rethink what young really means. A galaxy only a few 100 million years old might sound immature by human standards, but in cosmic terms, that may have been more than enough time for complexity to arise. When conditions are right, growth does not wait. This realization also reshapes how we think about cosmic milestones. The appearance of the first stars, the formation of the first galaxies, the reionization of the universe. These events were once placed neatly along a stretched timeline. Now, those markers seem to cluster closer together, as if the universe rushed through its early chapters before slowing into the more measured pace we observe today. There is a subtle elegance to this shift. It suggests that the universe's early years were not empty or hesitant, but vibrant and productive. The cosmos did not stumble into existence, it arrived with momentum. James Webb's role in this revelation is almost paradoxical. It does not change the universe, it does not influence what it observes, it simply listens more carefully to ancient light. And in doing so, it reveals that our previous silence may have been due not to absence, but to distance. Before Webb, we could not hear the universe clearly enough at these early times. Our instruments lacked the sensitivity. Our view was blurred now with clearer sight. The early universe appears louder, not in sound, but in activity. This raises deeper philosophical questions about observation itself. How many other assumptions about the universe are shaped not by reality, but by the limits of our perception? How many quiet areas were actually full of motion we simply could not see? James Webb is a reminder that cosmic history is not fixed in textbooks. It is provisional. It evolves as our tools evolve. Each new observation refines not only what we know, but how we interpret what we thought we knew. There is also an emotional dimension to this shift, subtle but present. Humanity has long imagined itself arriving late to a universe that took billions of years to get interesting. Webb's discoveries suggest that the universe was interesting almost immediately. We did not miss the beginning of complexity. Complexity was always there, woven into the fabric from the start. This does not diminish our place in the cosmos. If anything, it enhances it. We are part of a universe that did not hesitate to become rich and structured, a universe that embraced possibility early and often. As researchers continue to analyze Webb's data, they are cautious not to rush to conclusions. Science moves deliberately, especially when foundations are involved. But the direction is becoming clear. The early universe was not the gentle, slow-growing place we once imagined. It was dynamic, efficient, and capable of rapid creation. This does not invalidate existing theories. It challenges them to become more complete. Models of galaxy formation will adapt. Simulations will incorporate new parameters. The story will change not in its laws, but in its rhythm. The universe did not break the rules, it played them faster. And in this faster rhythm there is a quiet beauty. The idea that from the very beginning the universe was eager to express itself, to light up, to organize, to build. James Webb is not revealing chaos. it is revealing confidence. A cosmos that did not wait to become itself. As we continue this journey through rewritten cosmic history, one thing becomes increasingly clear. The universe has always been more capable than we imagined. And the deeper we look, the more it invites us to rethink not just how it began, but how we understand beginnings themselves. As scientists absorbed the growing evidence that galaxies formed earlier and faster than expected, attention began shifting toward a deeper layer of the problem. Not just when structures appeared, but how the universe allowed such rapid organization at all. The question was no longer limited to galaxies being too big or too early. It became a question about the underlying assumptions that shaped modern cosmology from the start. For decades, the standard cosmological model worked remarkably well. It explained the large-scale structure of the universe, the distribution of galaxies, the cosmic microwave background, and the expansion of space itself. Within that framework, the early universe was governed by a delicate balance between gravity pulling matter together and expansion pulling it apart. Structure emerged, but only gradually because gravity needed time to overcome expansion. James Webb is not overthrowing that balance, but it is revealing that the balance may have tipped sooner than expected. One of the most unsettling realizations is that the early universe may have crossed critical thresholds almost immediately after they became physically possible. Cooling, for example, is essential for structure. Hot gas resists collapse. Once gas cools, gravity can take over. Traditional models assumed cooling was slow in the early universe because heavy elements, excellent coolants, had not yet formed. But Webb's observations suggest cooling may have been far more efficient even with simple elements like hydrogen and helium. Under extreme early universe conditions, hydrogen itself may have cooled gas clouds more effectively than models predicted. Combined with high densities, this could have allowed gas to collapse rapidly into stars, bypassing long delays that simulations assumed were unavoidable. The universe may not have needed to wait for chemical complexity to begin building structure. This challenges a quiet assumption embedded in many models that complexity must emerge slowly because it requires preparation. Webb is showing that preparation may have been minimal. Once the universe expanded just enough to allow cooling, gravity may have acted decisively. Another issue lies in how astronomers interpret brightness. A galaxy's brightness is often used as a proxy for its mass and star formation rate. The brighter it is, the more stars it likely contains. But brightness also depends on how stars are distributed, how dust absorbs light, and how radiation escapes the galaxy. Early galaxies may have been structured in ways that allowed light to escape more efficiently, making them appear even more developed than they truly were. Even accounting for this, many galaxies still appear too massive to fit comfortably into existing timelines. Adjustments help, but they do not erase the discrepancy. This is where cosmology enters a subtle phase. Not a crisis, but a refinement. The data are not screaming that the universe is broken. They are quietly suggesting that some assumptions were oversimplified. Consider the role of mergers. Modern galaxies grow significantly through mergers, slowly combining with others over time. In the early universe, everything was closer together. Mergers could have happened rapidly and repeatedly, building large galaxies in short periods. What looks like a mature galaxy might actually be the product of intense accelerated assembly rather than slow internal growth. This possibility reframes early galaxies not as anomalies but as records of an exceptionally crowded cosmic environment. The early universe may have been less sparse and more interactive than we imagined. There is also growing interest in whether the initial distribution of matter was slightly different than assumed. The cosmic microwave background shows small fluctuations in density shortly after the Big Bang. These fluctuations seeded all later structure. If those fluctuations were slightly larger or structured differently on small scales, they could have led to faster collapse and earlier galaxy formation without violating known physics. James Webb cannot see the cosmic microwave background directly, but it can see the consequences of whatever patterns existed then. The early galaxies it observes may be the amplified echoes of those initial conditions. What makes this moment particularly powerful is how calm the revision process is. There are no dramatic declarations of failure, no urgent rewriting of textbooks overnight. Instead, there is a slow, collective recalibration. Papers are published with cautious language. Words like tension, unexpected, and requires further investigation appear again and again. This is science working as intended. The universe is not contradicting itself. It is revealing details we were previously blind to. There is also a humbling lesson about scale. Human intuition struggles with time spans of millions, let alone billions of years. When cosmologists say something happened quickly, they may still mean over tens of millions of years. From a human perspective, that is unimaginably long. From a cosmic perspective, it may be a blink. The early universe may have had more than enough time to produce complexity even within what we consider a narrow window. Our sense of too fast may be shaped more by intuition than by physics. James Webb's discoveries also encourage a shift in perspective about certainty. Cosmology often presents clean narratives, beginnings, eras, transitions. These narratives are useful, but they are approximations. The real universe does not organize itself into neat chapters. Processes overlap, timelines blur. Growth does not always follow smooth curves. What Webb is revealing may be less about errors and more about texture. The early universe may have been messier, more varied, and more efficient than our simplified models allowed. There is a deeper philosophical implication here as well. Humans tend to project linear stories onto everything: childhood, maturity, old age. We did the same with the universe. We imagined it growing slowly from a simple beginning into complexity. Webb suggests that complexity was never far away. It emerged almost as soon as conditions permitted. This does not make the universe less mysterious, it makes it more so. Because if the universe was capable of rapid organization from the start, then the seeds of complexity were not fragile accidents, they were robust features of reality. The laws of physics did not merely allow structure, they encouraged it. That realization reframes our relationship with cosmic history. We are not living in a universe that stumbled into order after billions of years of trial and error. We are living in a universe that was ready to organize itself almost immediately. James Webb is not rewriting cosmic history by contradiction, it is rewriting it by revelation. It is showing us that the early universe was not waiting for permission to become interesting. It took the first opportunity and ran with it. As data continues to accumulate, the story will sharpen. Some early galaxies may be reclassified, others will remain challenging, but the overall message is unlikely to disappear. The universe's youth was far more productive than we imagined. This is not unsettling because it undermines knowledge. It is unsettling because it expands it. It reminds us that our models are not mirrors of reality but maps, useful but incomplete. And James Webb, quietly collecting ancient light, is filling in those missing regions of the map. Not with noise or drama, but with patience. The same patience the universe itself seems to have had, even as it built stars, galaxies, and structure far sooner than anyone expected. Cosmic history is not being rewritten because it was wrong. It is being rewritten because it was incomplete. And with each new observation, the universe reveals that its earliest chapters were not tentative drafts, but confident opening statements written in light. As the picture of a rapidly forming universe becomes clearer, scientists are beginning to confront one of the most delicate aspects of this revision: the relationship between observation and interpretation. James Webb is not only showing us unexpected objects, it is forcing us to re-examine how we translate light into history. Every image Webb sends back is more than a photograph. It is a measurement, filtered through models that convert brightness, color, and spectral signatures into estimates of age, mass, and composition. Those models were built using assumptions that made sense before Webb existed. Now, those assumptions are being tested in a regime they were never designed for. One of the key challenges lies in understanding stellar populations in the early universe. When astronomers observe a distant galaxy, they do not see individual stars. They see combined light from billions of them. To interpret that light, they rely on models that predict how different mixtures of stars should appear at different ages. But if early stars were fundamentally different from those we see today, those predictions may be slightly off. The first generations of stars likely formed under extreme conditions. They were born in environments with almost no heavy elements, surrounded by dense gas and influenced by intense radiation fields. These conditions could have produced stars that were brighter, hotter, or shorter lived than typical stars today. If early stellar populations behaved differently, then galaxies could appear older or more massive than they truly were when interpreted using modern assumptions. James Webb is revealing light that may not fit neatly into familiar categories. This does not mean the data are wrong. It means the language we use to interpret the data may need to evolve. There is also the issue of dust. Dust plays a subtle but powerful role in shaping what we see. In the modern universe, dust absorbs and scatters light, often hiding star formation and altering the apparent colour of galaxies. In the early universe, dust was expected to be rare because it forms from heavy elements created in stars. Yet Webb is detecting signs of dust surprisingly early. If dust formed faster than expected, perhaps due to intense star formation or rapid supernova cycles, it could affect how we estimate distances and ages. Dust can make galaxies appear redder, mimicking the effects of great distance. Untangling these effects requires careful spectral analysis, and even then, uncertainties remain. What makes this process slow and cautious is the stakes. Cosmic history is not something scientists rewrite lightly. It is a framework that connects the Big Bang, the formation of galaxies, and the structure of the universe we observe today. Any revision must fit not only Webb's data, but also decades of observations from other telescopes, measurements of the cosmic microwave background, and precise tests of fundamental physics. So far, the emerging picture is not one of contradiction, but of compression. The same events still occur, but they may occur closer together in time. The universe did not skip steps, it simply moved through them faster. This idea is quietly profound. It suggests that the early universe was not a prolonged waiting room, but an active construction site. Gravity, cooling, star formation, and chemical enrichment may have worked in parallel, reinforcing each other rather than proceeding in isolation. James Webb is also prompting renewed interest in alternative pathways to galaxy growth. For example, cold gas streams flowing along cosmic filaments may have fed early galaxies continuously, allowing them to grow rapidly without relying solely on mergers. These streams, predicted by simulations but difficult to observe directly, could have been far more effective in the dense early universe. If such mechanisms were dominant, they would help explain how galaxies assembled mass so quickly without violating known laws of physics. Webb's observations may be the first indirect evidence that these processes were not just theoretical curiosities, but central drivers of early cosmic evolution. Another subtle shift concerns how astronomers think about uniformity. For a long time, models favoured averages, typical galaxies, typical growth rates, typical environments. But the early universe may have been more uneven than expected. Some regions could have evolved extremely rapidly, while others lagged behind. Webb's deep fields may be capturing the brightest, fastest growing systems simply because they are easiest to detect. If this is the case, then the early universe was not uniformly fast or slow, but diverse. Our view may be biased toward the most extreme examples. Understanding that bias is crucial, and researchers are actively working to quantify it. Yet even after accounting for bias, dust, stellar populations, and interpretation uncertainties, something remains unmistakable. The early universe was capable of producing complexity with remarkable speed. That capacity itself demands explanation. There is a deeper conceptual shift happening alongside these technical discussions. Cosmology has often emphasized the fragility of structure. Small changes in conditions can lead to vastly different outcomes. Webb's discoveries suggest something slightly different, a robustness in the universe's ability to organize itself. From this perspective, structure is not a delicate accident. It is a natural consequence of the universe's basic ingredients interacting under the right conditions. Once expansion slowed just enough and matter could cool, gravity took the lead, and the universe responded decisively. This view does not remove mystery, it relocates it. Instead of asking why structure exists at all, we are now asking why it appeared so quickly and what that says about the fundamental tendencies of nature. James Webb is acting as a mirror, reflecting not just ancient light, but the assumptions embedded in our theories. Some of those assumptions will hold, others will soften, a few may dissolve entirely. This is not a crisis. It is the normal, healthy evolution of understanding. There is also something deeply human about this moment. Every generation of astronomers inherits a universe that feels mostly known, with a few unanswered questions at the edges. Then a new instrument comes along and shifts the edges inward, revealing that what felt settled was only provisional. The early universe, once imagined as dim and uneventful, now appears vibrant and capable. That change in perception does not diminish the beauty of the cosmos, it enhances it, because a universe that could organize itself so quickly is a universe rich in potential. It suggests that complexity is not rare or fragile, but woven deeply into reality's fabric. As Webb continues to observe, the revisions will continue quietly. Papers will be refined, models will be adjusted. The story of cosmic history will gain sharper detail and deeper nuance. What remains unchanged is the sense of wonder, the realization that even at the very beginning, the universe was already doing more than we thought it could. James Webb is not rewriting cosmic history by erasing chapters. It is revealing footnotes we never knew were there, and in those footnotes, we are discovering that the universe's earliest moments were not tentative experiments, but confident acts of creation carried out at a pace that still humbles us today. As this revised picture of the early universe settles in, attention naturally turns toward one of the most foundational elements of cosmic history, the timeline itself. For a long time, cosmology relied on a comforting sense of order. The universe expanded, cooled, and slowly assembled structure in a sequence that felt measured and predictable. Each era followed the last with generous spacing, as though the cosmos were carefully pacing itself. James Webb is revealing that this sense of spacing may have been an illusion created by limited vision. When astronomers reconstruct the universe's past, they divide it into named epochs: recombination, the Dark Ages, cosmic dawn, reionization, galaxy assembly. These labels are useful, but they can give the impression that each stage unfolded in isolation. Webb's observations suggest something more fluid. These eras may have overlapped extensively, blending into one another rather than forming neat chapters. The first stars may have ignited while the universe was still emerging from darkness. Early galaxies may have assembled while reionization was already underway. Chemical enrichment may have progressed alongside structure formation rather than waiting its turn. Instead of a ladder, cosmic history may be more like a braided stream, with multiple processes flowing together at once. This realization forces scientists to rethink how quickly cause and effect operated in the young universe. In a dense environment, feedback loops can accelerate dramatically. Star formation produces radiation. Radiation alters gas behavior. Altered gas behavior leads to more star formation. What might take billions of years today could have unfolded in tens of millions of years under early conditions. Time itself, in a practical sense, may have behaved differently, not because physical laws changed, but because circumstances amplified their effects. Gravity did not become stronger, but it had more material packed into smaller volumes. Cooling did not become more efficient because new physics appeared, but because densities were higher and distances were shorter. James Webb's observations are quietly teaching us that the universe's early pace cannot be judged by modern standards. This has implications for one of the most important transitions in cosmic history. reionization. This was the period when the first stars and galaxies flooded the universe with radiation, stripping electrons from hydrogen atoms and transforming the cosmos from opaque to transparent. Reionization was once thought to be slow and gradual, stretched across hundreds of millions of years. Webb's data suggest it may have been faster and more uneven. Some regions may have reionized very early, powered by intense star formation in massive galaxies, while others lagged behind. The universe may have resembled a patchwork of light and darkness rather than a uniform glow spreading evenly. This unevenness matters. It means that early galaxies did not all experience the same environment. Some grew in regions already bathed in radiation. Others formed in pockets of relative darkness. These differences could have influenced how quickly galaxies evolved, further contributing to the diversity Webb now observes. Another consequence of a compressed timeline is the rapid buildup of heavy elements. Elements heavier than hydrogen and helium are forged inside stars and spread through space by stellar winds and explosions. Traditional models assumed that early galaxies would be metal poor, gradually enriching themselves over long periods. Yet Webb is detecting signs of chemical maturity surprisingly early. This suggests that massive stars formed, lived and died quickly, seeding their surroundings with heavier elements at an accelerated pace. The universe did not wait long to diversify its chemistry. This rapid enrichment would have profound effects. Heavy elements allow gas to cool more efficiently, which in turn promotes further star formation. Once again, a feedback loop appears. Early star formation begets conditions for even more star formation. The universe may have entered a self-reinforcing phase almost immediately after the first stars ignited. There is a tendency to think of such rapid development as unstable or chaotic, but Webb's observations do not support that view. The early universe appears energetic but not disorderly. Structures are present. Patterns exist. The same laws that govern today's galaxies were already shaping these ancient systems. This suggests that cosmic order does not require long preparation. It emerges naturally when the right conditions exist. There is also a subtle shift in how astronomers think about cosmic inevitability. If galaxies formed quickly and efficiently, it implies that large-scale structure was not a fragile outcome dependent on fine-tuned circumstances. It may have been a robust consequence of the universe's initial conditions. This has philosophical weight. It suggests that complexity was not a late accident, but an early expression of reality's tendencies. The universe did not slowly discover how to build. It already knew. James Webb's role in revealing this is almost gentle. There are no dramatic images of destruction or upheaval. Instead, there is quiet evidence accumulating in the infrared. Light stretched thin by expansion, carrying information from a time when the universe was still deciding what it would become. Each spectrum Webb records adds another constraint to our understanding. Each galaxy detected adds another data point. Together, they form a pattern that is difficult to ignore. The universe's early growth was not hesitant, it was decisive. This does not mean that all questions are answered. In fact, it opens new ones. Why did the universe favour such efficiency early on? Did small variations in initial conditions have outsized effects? Are there subtle aspects of physics that become important only under extreme early conditions? These are not questions that undermine cosmology. They enrich it. They push it toward greater depth and realism. There is also a lesson here about humility. Human narratives often assume that beginnings must be slow, uncertain and fragile. We project our own experiences onto the cosmos. James Webb is reminding us that the universe does not share our intuitions. Its beginnings may have been bold rather than tentative. The rewriting of cosmic history is therefore not a dramatic overturning, but a recalibration of tone. The universe's early chapters are not footnotes leading slowly toward interest. They are dense with action, creativity, and rapid transformation. As scientists refine their models, they are learning to let go of unnecessary assumptions while preserving what still holds. The Big Bang remains, expansion remains, gravity remains. What changes is the tempo. Cosmic history is becoming less like a long prelude and more like an opening movement played at full volume, not loud in sound but rich in activity. James Webb is allowing us to hear that movement more clearly for the first time, and as we listen we begin to understand that the universe did not take its time becoming complex. It simply waited until it could, and then it moved with astonishing confidence, building the foundations of everything that would follow in a surprisingly short span of cosmic time. As this emerging picture settles into the broader landscape of cosmology, scientists are beginning to confront a realization that feels subtle yet deeply transformative. The early universe may not have required special circumstances to become complex. Instead, complexity may have been the natural outcome of ordinary physics operating under extraordinary density and proximity. For a long time, cosmological models quietly assumed that the universe needed time to prepare itself. Matter had to cool, structures had to stabilize, processes had to slow down enough for order to emerge. That assumption shaped how simulations were built and how observations were interpreted. James Webb is revealing that this preparation phase may have been far shorter and far less tentative than imagined. One reason for this shift lies in the way gravity behaves in crowded environments. In the modern universe, galaxies are separated by enormous distances. Gas clouds often drift for millions of years before interacting strongly. But in the early universe, everything was closer together. Gravity did not need to reach across vast voids. It acted locally and decisively, pulling matter inward almost as soon as it could cool. This closeness fundamentally alters the pace of cosmic events. Processes that feel slow today may have been almost immediate in the early universe, not because gravity changed, but because the environment magnified its effects. The universe did not evolve faster because time flowed differently, but because conditions allowed physical processes to operate at full efficiency. James Webb's observations are forcing scientists to acknowledge that the early universe may have been operating at the upper limits of what known physics allows, not exceeding those limits, but approaching them. This realization reframes many long-standing puzzles. For example, the rapid appearance of supermassive black holes has troubled astronomers for years. Black holes grow by accreting matter, a process thought to be slow and regulated. Yet Webb has detected luminous quasars powered by massive black holes at extremely early times. Their existence seemed to require growth rates that bordered on the impossible. But if the early universe was denser, richer in gas, and less regulated by feedback mechanisms, then black hole growth may have been far easier than expected. Abundant material could have flowed inward continuously, allowing black holes to reach enormous masses quickly without violating physical constraints. In this light, the early universe appears less like a fragile balancing act and more like a system primed for rapid amplification. Small seeds could grow large very quickly. Initial advantages could compound dramatically. This compounding effect is important. Once a region begins forming stars efficiently, it produces radiation, metals, and gravitational wells that attract even more material. Growth accelerates. Webb's discoveries may be showing us galaxies caught in the midst of this acceleration phase. There is also a shift underway in how scientists think about cosmic normality. In earlier models, extreme objects were treated as exceptions. Massive galaxies, luminous quasars, chemically mature systems were expected to be rare at early times. Webb suggests they may have been common. If so, then what we considered extreme may have been ordinary in the universe's youth. Our sense of what is typical may be skewed by observing a much older, quieter cosmos today. This raises an intriguing possibility. The universe's most creative period may have occurred near its beginning. Not because laws were different, but because opportunity was abundant. Raw material was everywhere, interactions were frequent. Feedback had not yet slowed growth. James Webb is giving us a glimpse of that creative surge. There is also a growing awareness that our language may be limiting our understanding. Terms like early, primitive, and immature carry implicit judgments shaped by human experience. In the context of the universe, these words may mislead more than they clarify. An early galaxy does not have to be simple. A young universe does not have to be quiet. Age and complexity are not inherently linked. This conceptual shift has consequences beyond astrophysics. It affects how we think about cosmic inevitability. If structure formed rapidly and robustly, then the emergence of complexity may be a common feature of universes like ours, not a delicate accident balanced on a knife's edge. That idea resonates quietly with broader questions about existence. It suggests that the universe, once set in motion, naturally tends toward organization under the right conditions. Complexity is not forced, it emerges. James Webb is not making this claim explicitly. It is simply providing evidence that challenges the need for slow, fragile explanations. As researchers work through this evidence, they are carefully re-evaluating simulations of the early universe. Models are being adjusted to allow faster cooling, more efficient star formation, and earlier feedback. Some simulations already show that when these factors are tweaked within realistic bounds, galaxies resembling Webb's observations can indeed form quickly. This is encouraging. It suggests that the universe is not asking for entirely new physics. It is asking for a more complete understanding of how known physics behaves under extreme conditions. There is patience in this process. No single explanation has yet emerged as definitive. Instead, there is convergence toward a picture in which multiple factors align: dense environments, efficient cooling, rapid star formation, early mergers, and delayed feedback. Together, these factors create a universe capable of surprising speed. James Webb's role is to anchor these ideas in observation. It provides constraints that models must respect. It narrows the space of possibilities, guiding theory without dictating it. This interplay between observation and theory is where science is most alive. It is not a battle between ideas and data, but a conversation. The universe speaks through light. Scientists respond through models. The dialogue continues. There is also something quietly reassuring in this moment. The laws of physics are not failing. They are revealing their depth. What once seemed like rigid limitations now appear as flexible frameworks capable of producing richness under the right conditions. The rewriting of cosmic history, then, is not about correcting errors. It is about learning how to read the story more accurately. The words were always there. The ink was written in light. We simply lacked the clarity to see it. James Webb has sharpened our vision. As we move forward, the early universe no longer feels distant or abstract. It feels active, capable, and expressive. Not a blank canvas waiting for detail, but a dynamic system already exploring its possibilities. This realization changes how we think about beginnings. They are not always slow. They are not always fragile. Sometimes beginnings are decisive. The universe's beginning may have been one of those moments. And as James Webb continues to observe, it will keep revealing a past that is not quieter than expected, but fuller. Not simpler, but richer. Not hesitant, but confident. Cosmic history is becoming less like a gradual awakening and more like an immediate expression of what the universe was always capable of being. In that sense, James Webb is not just rewriting history, it is reminding us that the universe, from its very first moments, may have been far more awake than we ever imagined. As this deeper understanding takes shape, cosmologists are beginning to reflect on something even more fundamental than timelines or mechanisms, the assumptions that guided the questions in the first place. For generations, the early universe was treated as a fragile stage, one where small changes could easily derail structure. That perspective shaped how scientists asked questions, framed hypotheses, and interpreted evidence. James Webb is quietly encouraging a different mindset, one in which the universe's earliest moments were not precarious but resilient. This shift matters because it changes what kinds of explanations feel plausible. If the early universe was robust rather than delicate, then rapid organization does not need to be explained away as an anomaly. It becomes a natural outcome of conditions that favored growth. Gravity did not struggle against expansion, it exploited density. Cooling did not cool, it accelerated when given the chance. Structure did not tiptoe into existence, it emerged as soon as it could. One way to see this is by reconsidering the role of randomness. In many older models, early structure formation depended heavily on rare fluctuations, chance over densities that happened to collapse before others. This made early massive galaxies feel improbable, almost lucky. Webb's observation suggests something else, that the environment itself may have made such outcomes common. The early universe may have reduced the role of luck by amplifying small differences quickly and consistently. In that context, the early cosmos begins to resemble a system tuned for amplification. Minor variations did not remain minor, they grew, merged, and reinforced one another. Once the first stars ignited, they altered their surroundings in ways that encouraged further activity. Radiation heated some regions while compressing others. Supernovae enriched gas while also triggering new collapses nearby. Nothing acted in isolation. This interconnectedness is key. Modern astrophysics often studies processes separately: star formation, feedback, mergers, cooling, because that is how problems become manageable. But the early universe did not separate its processes so neatly. Everything happened at once, layered and interacting. Webb's data are revealing the combined result of those interactions, not their individual steps. There is also a growing appreciation for how scale influences behavior. On the largest scales, the universe is smooth and uniform. On smaller scales, it is clumpy and dynamic. The early universe existed at a unique intersection of these regimes. It was globally expanding, yet locally dense. That combination allowed gravity to act decisively without immediately being diluted by expansion. In practical terms, this means that early galaxies did not have to fight the universe to grow. They grew with it. James Webb is also changing how scientists think about uncertainty. In the past, uncertainty in early universe observations was dominated by lack of data. Now, uncertainty arises from interpretation. We can see the objects clearly, but translating what we see into histories requires models that are still being refined. This is a different kind of challenge, and in many ways a more productive one. It means that observation is no longer the bottleneck, understanding is. As researchers work through this challenge, they are finding that many tensions can be eased without dramatic revisions. Small adjustments applied consistently can reshape the narrative. Faster cooling here, earlier mergers there, slightly different initial conditions. Together, these changes accumulate into a universe that looks much more like the one Webb is revealing. There is also an emerging awareness that cosmic history may not be best described by a single universal timeline. Different regions may have evolved at different speeds. Some may have raced ahead, forming massive galaxies early. Others may have remained quiet longer. Webb's deep fields capture only a fraction of this diversity, biased toward the brightest and most active systems. This regional variation adds texture to the story. The early universe was not monolithic. It was patchy, uneven, and diverse. Some places lit up early and intensely, others lagged behind. Over time, these differences blended, producing the more uniform cosmic landscape we see today. This idea resonates with how complexity often emerges in other systems. Growth is rarely uniform. It clusters. It accelerates locally. It spreads outward. The universe may not be so different in this respect. James Webb's observations also prompt reflection on how knowledge progresses. Each generation of instruments expands the observable universe, not just spatially, but conceptually. What once lay beyond reach becomes visible, and with it, assumptions are tested. There is a humility embedded in this process. Scientists do not cling to outdated models out of pride. They adapt, they revise, they learn. The rewriting of cosmic history is not an admission of failure, but a sign that understanding is alive. This moment also underscores the importance of patience. Webb's data will be analysed for decades. Early interpretations will be refined. Some early surprises may soften, others may deepen. The story will evolve slowly, guided by evidence rather than excitement. That slow evolution mirrors the tone of the universe itself. Even when things happen quickly in cosmic terms, they unfold over timescales that dwarf human experience. Webb's discoveries feel sudden to us because they arrive compressed into years rather than eons. There is something almost poetic in that contrast. A universe that built complexity rapidly over millions of years is now being understood slowly over decades by a species that exists for barely a moment. James Webb's role in this unfolding understanding cannot be overstated. It is not just a more powerful telescope, it is a bridge between expectation and reality. It allows us to see the universe not as we assumed it was, but as it actually was. And what it shows is a cosmos that did not hesitate. This realization invites a deeper sense of connection. The same universe that organized itself efficiently in its youth eventually produced stars like our Sun, planets like Earth, and minds capable of wondering how it all began. The speed and confidence of early structure formation did not preclude reflection. It made reflection possible. As cosmologists continue their work, they are learning to let the universe lead the story. Instead of forcing observations to fit expectations, expectations are being reshaped to fit observations. This is science at its most honest. There is no sense of panic in this rewriting, no rush to declare revolutions. Instead, there is careful listening. Ancient light arrives. Instruments record it. Minds interpret it. Models adjust. Understanding deepens. James Webb is teaching us that the universe's earliest moments were not tentative sketches. They were bold strokes, laid down with remarkable efficiency. The cosmos did not wait to become structured, it became structured as soon as it could. That lesson extends beyond astrophysics. It reminds us that beginnings are not always fragile. Sometimes they are powerful, sometimes they carry within them the full potential of what will follow. The early universe, as revealed by James Webb, appears to have been one of those beginnings. And as this story continues to unfold, one truth is becoming clear. The universe did not need billions of years to learn how to build. It knew from the start. James Webb is simply showing us that we are finally ready to see it. As this revised understanding settles more deeply into cosmology, attention begins to turn toward a question that feels almost philosophical, yet is rooted firmly in physics. If the universe was capable of organizing itself so efficiently, so early, what does that reveal about the nature of cosmic order itself? For a long time, order was treated as something that emerges slowly from disorder. The early universe, hot and dense, was imagined as a kind of formless starting point that gradually cooled into structure. Complexity, in this view, was something earned over time. James Webb is suggesting a subtler truth. Disorder and order may not be opposites in the way we intuitively think. Under the right conditions, they may coexist, with structure emerging naturally from apparent chaos. The early universe was certainly energetic and extreme, but it was not random. It followed precise physical laws from its very first moments. Expansion, gravity, radiation, and quantum fluctuations were already shaping outcomes. Webb's observations hint that these ingredients did not need prolonged refinement. They were already sufficient. This realization reframes how scientists think about inevitability. If the early universe consistently produced large galaxies, massive stars, and complex structures, then such outcomes may not have been rare accidents. They may have been likely, even expected. The universe may have had a built-in tendency toward organization, not because of fine-tuning, but because of how its fundamental components interact. James Webb's discoveries also deepen our understanding of cosmic scale. When astronomers speak of early galaxies forming quickly, they often mean within a few 100 million years. That may sound long by human standards, but in cosmic terms it is remarkably brief. The universe is more than 13 billion years old. If complex galaxies formed within the first few percent of that time, then the bulk of cosmic history has been spent refining, rearranging, and evolving structures that appeared very early on. This suggests that the universe's creative phase may have been front-loaded. The most dramatic construction may have occurred early, followed by a long period of adjustment and stabilization. In that sense, cosmic history resembles a rapid burst of creativity followed by a long, slow unfolding. James Webb is offering a window into that burst. There is also an emerging appreciation for how perception shapes theory. Before Webb, the faintness of early galaxies made them difficult to study. Observations were sparse, uncertain, and biased toward the brightest objects. This scarcity encouraged cautious, conservative models. Webb has transformed scarcity into abundance. Suddenly, early galaxies are numerous and detailed. With abundance comes confidence, not in conclusions, but in exploration. Scientists can now compare many early galaxies rather than relying on a handful. Patterns emerge. Variations become meaningful. Outliers stand out clearly. This statistical richness strengthens the case that rapid early structure formation was widespread, not exceptional. Another layer of insight involves how cosmic environments influence development. The early universe was not uniform. Some regions were denser than others, some collapsed sooner, some ignited stars earlier. Webb's observations capture this diversity. They show that while many galaxies formed early and quickly, others may have followed slower paths. This diversity matters because it suggests that cosmic history is not a single story, but many overlapping ones. The universe did not evolve at one speed everywhere. It evolved at many speeds simultaneously, shaped by local conditions within a shared framework of physical laws. James Webb's role is to reveal these local stories in greater detail. Each galaxy observed is not just a data point, but a record of how particular conditions played out. Together, they form a mosaic of early cosmic life. There is also a growing sense that our previous narratives may have underestimated the universe's capacity for self-regulation. Rapid growth does not necessarily lead to runaway chaos. Feedback mechanisms, even if delayed, eventually emerge. Radiation heats gas, black holes influence their surroundings. Over time, growth slows, structures stabilize, and the universe transitions into a calmer phase. Webb may be capturing the universe near the peak of its youthful exuberance, before regulation fully set in, but after the basic framework was established. This perspective offers a satisfying continuity between the early universe and the one we inhabit today. The laws did not change. The environment did. The universe moved from a dense, crowded, fast-paced state into a more spacious, measured one. Complexity did not vanish, it simply evolved under new conditions. There is also a quiet lesson here about expectation. Humans often assume that beginnings must be tentative, fragile, and uncertain because our own beginnings often are. But the universe is not human. Its beginnings may have been confident because the rules were already in place. James Webb is reminding us that the universe does not need to learn how to exist. It begins already knowing. This insight influences how scientists frame future questions. Instead of asking why structure appeared at all, the focus shifts toward understanding the precise pathways it took. The emphasis moves from possibility to mechanism. This is a healthier place for cosmology to be. It reflects a maturity in the field where the existence of structure is taken as given, and the challenge lies in tracing its detailed history. James Webb's data will continue to refine this challenge. As more observations accumulate, models will sharpen, uncertainties will shrink. Some early surprises may find elegant explanations within known physics. Others may require deeper insight. But the overall direction seems clear. The early universe was not waiting, it was acting. There is something quietly inspiring in that realization. It suggests that complexity, once allowed, does not hesitate. It unfolds, it explores, it builds. The rewriting of cosmic history, then, is not about correcting a mistake. It is about recognizing a capacity that was always there. The universe did not stumble into galaxies and stars after billions of years of trial. It moved toward them decisively as soon as conditions permitted. James Webb has given us the privilege of seeing that decisiveness, and in doing so, it has shifted our sense of cosmic time. The early universe is no longer a distant, dim prologue. It is a vibrant chapter filled with action, creativity, and rapid transformation. As we continue this journey through revised cosmic history, one truth grows steadily clearer. The universe has always been more capable than we imagined, not just now, but from the very beginning. James Webb is not telling us that our story was wrong. It is telling us that the story was always richer, faster, and more confident than we thought. And as we listen more carefully to the ancient light it collects, we are learning to read the universe's opening chapters with fresh eyes, not as hesitant drafts, but as bold statements written across space and time. As this understanding deepens, scientists are beginning to recognize that James Webb's impact goes beyond revising dates and growth rates. It is reshaping how we think about cosmic causality itself, the idea that certain events must happen before others can follow. The traditional narrative assumed a strict order. Stars must form before galaxies become large. Metals must accumulate before cooling becomes efficient. Black holes must grow slowly before influencing their surroundings. Webb's observations suggest that many of these processes may have unfolded together, intertwined rather than sequential. In the early universe, boundaries between cause and effect may have been less rigid than our models assumed. Star formation, chemical enrichment, and black hole growth could have reinforced one another almost immediately. A burst of star formation enriches gas with heavier elements. That enrichment allows gas to cool faster. Faster cooling leads to more star formation. Meanwhile, dense regions feed nascent black holes, whose radiation reshapes their surroundings. What looks like a sequence in hindsight may have been a tightly coupled system evolving as a whole. This coupling is important because it changes how scientists interpret impossible objects. When something appears too massive, too bright, or too mature for its age, the problem may not be that it violates physics, but that our mental separation of processes is artificial. The universe may not respect the neat categories we impose on it. James Webb is offering evidence that the early cosmos was a place of simultaneity rather than succession. This realization has implications for how cosmologists approach simulations. Many simulations are built in stages, with parameters adjusted as one process hands off to another. Webb's data are encouraging more holistic approaches where multiple feedback loops operate together from the start. These models are computationally demanding, but they are better suited to capturing the complexity Webb is revealing. There is also renewed attention on the role of scale in shaping causality. In a dense early universe, local events could have global consequences more easily. A starburst in one region could influence neighboring regions quickly because distances were small. Radiation did not need to travel far to matter. The universe was compact enough that cause and effect propagated efficiently. This efficiency may explain why early structure formation appears so coordinated. The universe did not need long delays for information to spread. Conditions change rapidly and collectively. James Webb's observations also prompt a re-evaluation of how certainty accumulates in science. Early interpretations often rely on individual examples. As Webb's catalogue of early galaxies grows, patterns become harder to dismiss. Statistical weight replaces anecdote. What once felt surprising begins to feel characteristic. This transition is subtle but powerful. It marks the difference between anomaly and trend. Another aspect of this rewriting involves cosmic humility. For years, cosmologists felt confident that the broad outline of cosmic history was settled, with only details left to refine. Webb is demonstrating that even the outline can evolve. This does not weaken the field, it strengthens it by reminding scientists that understanding is always provisional. There is a calm confidence in how the scientific community is responding. Instead of resisting the data, researchers are leaning into it. Workshops are organized, papers are written, collaborations expand. The universe is being listened to more carefully, not argued with. James Webb is also reshaping how the public encounters cosmic history. Images of ancient galaxies, once abstract concepts, now appear vivid and immediate. This visibility brings the early universe closer, not just scientifically, but emotionally. It becomes easier to imagine a cosmos already alive with activity billions of years ago. That emotional shift matters. It changes how we relate to cosmic time. The early universe no longer feels like a distant prelude disconnected from the present. It feels like a dynamic ancestor whose choices shaped everything that followed. There is also an emerging sense that the universe's ability to organize itself early may have influenced its long-term trajectory. Rapid early structure formation could have set initial conditions that guided later evolution. Large galaxies formed early may have dominated their environments, influencing the growth of neighboring systems. Early black holes may have seeded the centers of galaxies we see today. In this way, the early universe's efficiency may echo through billions of years, shaping cosmic history long after the initial burst of activity faded. James Webb's discoveries encourage scientists to think in terms of continuity rather than separation. The universe did not reset between eras. Each phase flowed into the next, carrying forward momentum and structure. This continuity challenges the idea that cosmic history is a series of clean transitions. Instead, it may be better understood as a spectrum, with overlapping processes gradually shifting in dominance. Webb is illuminating those overlaps. There is also a renewed interest in questioning how typical our cosmic environment really is. If the universe formed structure quickly and robustly, it raises questions about how common similar histories might be elsewhere. While we have no evidence of other universes, understanding how ours evolved informs broader discussions about cosmic possibility. James Webb does not answer these questions. It reframes them. By revealing a universe that organized itself early and confidently, Webb invites us to reconsider what we mean by cosmic maturity. Perhaps maturity is not something achieved slowly over time, but something that emerges naturally once basic conditions are met. This idea resonates beyond astrophysics. It reflects a broader pattern seen in complex systems where structure can emerge rapidly when thresholds are crossed. The universe may be the ultimate example of such a system. As researchers continue to analyze Webb's data, they are developing new tools, new models, and new intuitions. The rewriting of cosmic history is not a single event, but an ongoing process. Each new observation adds nuance, depth, and clarity. What remains constant is the sense of wonder, the realization that the universe, even in its earliest moments, was already expressing its potential. It did not wait for permission. It did not require long rehearsal. It acted. James Webb is not telling us that the universe behaved unexpectedly. It is telling us that our expectations were shaped by incomplete information. Now that the information has expanded, so too must our understanding. The early universe is no longer a dim, uncertain beginning. It is a vibrant, efficient, interconnected system whose complexity emerged as soon as it could. And in recognizing this, we are not diminishing the mystery of cosmic history, we are deepening it. Because a universe that could build so much so quickly invites a new kind of curiosity, not about what went wrong, but about how much more there is to learn. James Webb has opened that door quietly, and as we step through it, we find a cosmic history that is not simpler than we imagined, but richer, faster, and more alive than we ever expected. As this deeper picture of the early universe comes into focus, scientists are beginning to reflect on a subtle but far-reaching consequence of everything James Webb has revealed: the way we think about confidence in cosmic knowledge. For decades, cosmology felt like a field approaching completion. The broad outline seemed secure. The early universe was hot, simple, and dim. Complexity followed later. Details remained uncertain, but the story itself felt stable. James Webb has shown that stability was partly an illusion. not because the core ideas were wrong, but because they were incomplete. The universe, it turns out, was already expressing complexity before we expected it to, and doing so repeatedly. This realization shifts the tone of cosmology from one of quiet closure to one of renewed openness. There is a difference between knowing the rules of a game and understanding how the game actually plays out. For a long time, cosmologists knew the rules: gravity, expansion, nuclear fusion, radiation. What James Webb is revealing is that the universe played those rules more creatively than anticipated, especially in its earliest moments. This creative freedom does not violate physics, it exploits it. One of the most important lessons emerging from Webb's observations is that possibility space in the early universe was much larger than assumed. Models often focus on average outcomes, smoothing over extremes. Webb is showing that extremes may have been common. The universe may have explored its options rapidly, producing massive galaxies, intense starbursts, and early black holes as natural outcomes rather than rare exceptions. This has implications for how scientists define normal. What we observe today may represent a quiet, stabilized phase of cosmic evolution. The early universe, by contrast, may have been far more experimental. Conditions changed quickly. Feedback loops had not yet settled into equilibrium. Growth was not carefully regulated. In such an environment, the universe may have tested many configurations early on, with some persisting and others fading. The systems that survived became the ancestors of today's galaxies. James Webb is allowing us to see the survivors. This perspective reframes the early universe not as a blank canvas, but as a dynamic laboratory. It was not passively cooling while waiting for structure to emerge. It was actively building, combining, enriching, and reorganizing matter at a pace that challenges our intuition. There is also a shift underway in how scientists think about predictive power. Cosmological models have always aimed to predict what the universe should look like at different times. Webb's discoveries remind us that prediction is constrained by imagination. Models reflect not just physics, but the assumptions we bring to them. When assumptions are too conservative, predictions become narrow. Webb is expanding that narrowness. This does not diminish the value of models. It makes them more honest. It encourages broader parameter spaces, more flexible frameworks, and greater humility in interpretation. Instead of asking whether observations match expectations, scientists are increasingly asking whether expectations were too limited to begin with. This shift has practical consequences. New simulations are being designed to allow faster early growth. Feedback is being treated as a spectrum rather than a switch. Star formation is being modelled under a wider range of conditions. The goal is no longer to force early galaxies into old boxes, but to build boxes that can accommodate what Webb actually sees. There is also a renewed appreciation for uncertainty as a productive force. In science, uncertainty is often framed as a problem to be eliminated, but uncertainty also signals where discovery is most likely. James Webb has expanded uncertainty in the most fruitful part of cosmic history, the beginning. This expanded uncertainty is not chaos, it is opportunity. Another quiet consequence of Webb's work is the way it blurs the boundary between observation and interpretation. When data was sparse, interpretation dominated. Now that data are abundant, interpretation must slow down. Each image carries so much information that rushing to conclusions risks oversimplification. This encourages a slower, more reflective approach to cosmic history, one that values patience over certainty, one that allows multiple explanations to coexist while evidence accumulates. In this sense, James Webb is influencing not just what we know, but how we know. It is nudging cosmology toward a more contemplative mode, where the universe is listened to rather than interrogated. There is also a human dimension to this shift. The story we tell about the universe influences how we see ourselves. A universe that took billions of years to become interesting can feel distant and indifferent. A universe that expressed complexity almost immediately feels more intimate, more responsive, more alive. This does not imply intention or purpose. it implies capability. The same physical laws that allowed early galaxies to form rapidly eventually allowed stars like the Sun to shine steadily, planets like Earth to form, and life to emerge. The efficiency of early structure formation may have set the stage for everything that followed. James Webb is reminding us that the universe did not stumble into habitability by accident. It built the conditions for complexity early, then spent billions of years refining them. There is also a subtle emotional resonance in seeing ancient galaxies so clearly. Their light has travelled for more than 13 billion years to reach us. It left when the universe was young, dense and busy. Now it arrives in a universe that is older, larger and quieter. That contrast carries meaning. It reminds us that we are living in a late chapter of a very long story. The most dramatic construction may already be behind us. What remains is evolution, adaptation and slow change. James Webb gives us access to that earlier chapter, not to romanticize it, but to understand it. As researchers continue to analyze Webb's findings, they are careful to avoid overstatement. No single observation overturns decades of work. No single galaxy forces a complete rewrite. But taken together, the evidence points in a consistent direction. The universe's early history was more active, more efficient, and more interconnected than previously believed. This direction matters because it reshapes future questions. Instead of asking why the universe formed structure at all, scientists now ask how it did so quickly and what that speed reveals about fundamental physics. These questions will guide research for years, perhaps decades. James Webb is not delivering final answers. It is opening pathways. There is something fitting about this. The telescope itself is a product of patience, collaboration, and long-term vision. Its discoveries encourage the same qualities in interpretation. Cosmic history is not being rewritten in haste. It is being rewritten carefully, line by line, observation by observation. What emerges is a story that feels less tentative and more confident, a universe that did not wait to express itself, a cosmos that began building as soon as it could, using simple rules to produce astonishing richness. James Webb has not made the universe stranger than it already was, it has made it more honest, and in that honesty we find not discomfort but clarity. The universe was never obligated to conform to our expectations. It was only obligated to follow its own laws. Now that we can see more clearly, those laws appear not as constraints but as enablers. They allowed a young universe to move quickly, decisively and creatively toward structure. The rewriting of cosmic history, then, is not about correcting a mistake. It is about adjusting our perspective to match reality. The universe did not change. We did. And as James Webb continues to send back ancient light, that adjustment will continue, slowly refining our understanding of how everything we see today emerged from a beginning far more capable than we ever imagined. As this revised understanding settles more firmly into the foundations of cosmology, scientists are beginning to reflect on what this means for the idea of limits in the universe. For many years, models of the early cosmos were shaped by what seemed reasonable, cautious, and constrained. Growth could not be too fast. Structure could not appear too early. Complexity required patience. James Webb is showing that many of these limits were not imposed by physics, but by expectation. This realization does not undermine scientific rigor, it sharpens it. The early universe, as revealed by Webb, appears to have operated close to the boundaries of what known physics allows. Gas cooled efficiently, gravity acted decisively, star formation proceeded rapidly, black holes grew with surprising speed. Yet none of this requires new laws or exotic forces. It requires only that we allow known processes to operate under extreme but natural conditions. This challenges a subtle habit in scientific thinking, the tendency to underestimate how much can happen when everything aligns. In the dense early universe, alignment was common. Distances were short, radiation fields were intense, feedback mechanisms had not yet fully developed to regulate growth. Under such circumstances, the universe may have expressed its full creative capacity quickly. before settling into a slower, more regulated phase. James Webb is revealing that this creative phase was not marginal, it may have been central. One consequence of this realization is a renewed focus on how early conditions set long-term trajectories. If galaxies formed rapidly and reached significant mass early, they would have shaped their environments for billions of years afterward. Their gravity would influence neighboring systems, their radiation would affect gas cooling, their black holes would sculpt galactic centers. In this sense, early efficiency may not have been a temporary curiosity, it may have been a defining influence that echoed through cosmic history. This perspective encourages scientists to think less in terms of isolated epochs and more in terms of legacy. The early universe did not simply pass into the later universe, it seeded it. The choices made by physical processes in those first few 100 million years constrained what was possible afterward. James Webb's discoveries suggest that many of the structures we see today are not the result of slow accumulation alone, but of early momentum carried forward. There is also a growing appreciation for how much of cosmic history may be invisible without the right tools. Before Webb, the early universe was represented by a handful of faint detections and indirect measurements. Those data supported cautious models. Now, with a flood of new information, the universe looks more active simply because we can finally see it. This raises an important philosophical point. Absence of evidence is not evidence of absence. The early universe was always busy. We just lacked the means to observe it. James Webb is correcting a perceptual gap, not a physical one. This correction has consequences for how scientists evaluate confidence in other areas of cosmology. It encourages humility when extrapolating beyond observable limits. If the early universe turned out to be more dynamic than expected, other unseen regimes may also hold surprises. There is also a renewed interest in how cosmic history might look different if observed from another vantage point. Our observations are constrained by light travel time, wavelength sensitivity, and instrument design. Webb has expanded that window, but it is still only one window. The universe may contain additional layers of activity beyond even Webb's reach. This realization reinforces the idea that cosmology is not converging toward a final story, but toward deeper layers of understanding. James Webb's influence extends beyond data. It is shaping how scientists ask questions. Instead of asking whether early galaxies should exist, the question becomes how they form so effectively. Instead of asking whether timelines are violated, the focus shifts to understanding why the universe favored such rapid organization. This reframing is powerful because it aligns inquiry with evidence rather than expectation. There is also a subtle emotional shift in the field. Surprise gives way to curiosity. Tension gives way to exploration. What initially felt like a challenge to established models now feels like an invitation to refine them. James Webb is not forcing scientists to abandon cosmic history. It is encouraging them to enrich it. This enrichment includes acknowledging uncertainty without discomfort. In many scientific disciplines, uncertainty is treated as something to eliminate. In cosmology, uncertainty often signals that the universe is revealing new structure. Webb's discoveries expand uncertainty in productive directions. They also expand wonder. Seeing massive galaxies where none were expected does not diminish our understanding. It deepens our appreciation for how capable the universe has always been. It reminds us that physical laws are not just constraints, they are generative. This generative quality may be one of the most important lessons emerging from Webb's observations. The universe did not merely permit structure, it encouraged it. Once the conditions were right, structure flourished. There is a quiet elegance in this idea. It suggests that complexity is not a rare achievement. It is a natural expression of reality under the right circumstances. James Webb is showing us those circumstances in unprecedented detail. As analysis continues, some early interpretations will inevitably be refined. Distances may be adjusted, mass estimates may change, some galaxies may turn out to be less extreme than initially thought, but even conservative revisions are unlikely to erase the broader trend. The early universe was active and capable. This robustness matters. It suggests that the universe's early behavior is not sensitive to minor uncertainties. The overall picture remains one of rapid, confident organization. That confidence carries forward into how scientists think about the future of cosmology. Webb is not the end of observation, it is a beginning. Its discoveries will guide the design of future instruments, inform new theoretical frameworks, and shape research priorities for decades. The rewriting of cosmic history, then, is not a moment, it is a process. A process grounded in evidence, guided by humility, and driven by curiosity. What James Webb has revealed so far is enough to change how we speak about the universe's beginnings, no longer as a long, hesitant prelude, but as an opening act filled with energy, creativity, and momentum. This does not make the universe less mysterious, it makes it more alive. And as scientists continue to listen to the ancient light arriving from the universe's earliest epochs, they are learning to tell a story that honors what the data reveal rather than what intuition once assumed. A story in which the universe did not wait to become complex. It became complex as soon as it could. James Webb is helping us see that clearly for the first time. And in doing so, it reminds us that the universe has always been more capable than we imagined, not just now, but from the very beginning. As this growing body of evidence reshapes how scientists understand the early universe, attention naturally turns toward the meaning of cosmic readiness. The idea that the universe may have been prepared for complexity almost from the moment it began. For many years, cosmology treated readiness as something earned gradually. Conditions had to evolve. Thresholds had to be crossed carefully. Time itself was seen as the primary ingredient that allowed structure to emerge. James Webb is suggesting something quieter and more profound, that readiness may have been built into the universe from the start. This does not imply design or intention. It implies that the fundamental laws governing matter, energy, and space were already sufficient to produce order once the initial chaos of expansion settled just enough. The universe did not need new rules to become complex. It needed only the opportunity to express the rules it already had. One way to understand this is to consider how little had to change before structure could form. Once the universe cooled enough for neutral atoms to exist, light could travel freely. Once gas could cool and lose pressure, gravity could act. These transitions happened quickly in cosmic terms, and once they occurred, the universe responded decisively. James Webb is revealing the results of that response. This perspective shifts how scientists think about inevitability. If complexity arises naturally and quickly under broad conditions, then the universe's development was not a delicate sequence that could easily have failed. It was a robust unfolding. Many paths could have led to structure, and the universe explored them efficiently. This robustness helps explain why Webb keeps finding early galaxies that look too mature. They are not exceptions. They are expressions of a universe that did not hesitate once it could act. There is also an important shift in how astronomers interpret early cosmic diversity. Webb's observations show that not all early galaxies are the same. Some are compact and intense, others are diffuse. Some show signs of rapid star formation. This variety suggests that the early universe was not following a single script. Instead, it was experimenting. Different regions experienced different conditions. Slight differences in density, temperature, or radiation could lead to very different outcomes. The universe did not enforce uniformity, it allowed diversity. This diversity is a hallmark of complex systems. When rules are simple but interactions are many, outcomes multiply. The early universe appears to have been exactly such a system. James Webb's ability to capture this diversity is transformative. It allows scientists to move beyond averages and study distributions. Instead of asking what a typical early galaxy looked like, researchers can ask how many different kinds existed and why. This shift from typicality to variety is subtle but powerful. It changes the kinds of questions scientists ask and the kinds of explanations they consider satisfying. Another important implication involves cosmic memory. The early universe did not reset itself between phases. The structures formed early influenced everything that followed. Galaxies that formed quickly became anchors for later growth. Black holes seeded early became the centers of galaxies that still exist today. Chemical enrichment initiated early shaped later star formation. In this way, the universe carries memory forward. The early efficiency revealed by Webb did not fade away. It shaped the entire arc of cosmic history. This continuity challenges the idea that cosmic history can be neatly divided into independent chapters. Instead, it appears more like a continuous flow, where early choices constrain later possibilities. James Webb is helping scientists trace that flow backward with unprecedented clarity. There is also a renewed appreciation for the role of uncertainty in shaping scientific narratives. Early models of the universe were necessarily cautious because they were built with limited data. That caution solidified into expectation. Webb is now revealing that those expectations may have been too conservative. This does not reflect a failure of earlier scientists. It reflects the natural limits of observation. Science advances by replacing absence with evidence. James Webb is replacing absence. This process also highlights the difference between explanation and understanding. Explanation often aims to simplify. Understanding accepts complexity. Webb is pushing cosmology toward understanding by showing that the universe's early behavior cannot be captured by a single tidy narrative. Instead, multiple processes acted together: cooling, collapse, star formation, feedback, enrichment, and mergers all overlapped. The early universe was not a sequence of steps, but a web of interactions. This web-like behavior aligns with patterns seen in many natural systems. Ecosystems, economies, and neural networks all exhibit emergent complexity when many simple components interact. The universe itself may be the ultimate example of emergence. James Webb is giving us a glimpse of emergence on the largest possible scale. This realization also reframes how scientists think about surprise. Surprise is not evidence that something is wrong. It is evidence that understanding has expanded beyond previous boundaries. Webb's discoveries feel surprising because they reveal regions of possibility that were previously unexplored. There is a quiet maturity in how the scientific community is responding. Instead of dismissing Webb's findings or rushing to radical conclusions, researchers are methodically exploring explanations that remain grounded in known physics. They are allowing the data to lead. This patience mirrors the pace of the universe itself. Even when events unfold rapidly in cosmic terms, understanding unfolds slowly in human terms. There is also an emotional undertone to this moment. Seeing a universe that organized itself quickly can inspire a sense of connection. It suggests that the universe has always been dynamic, expressive, and capable. The same forces that built early galaxies are still at work today, quietly shaping stars and planets. James Webb is reminding us that we are not living in a universe that slowly stumbled into meaning. We are living in a universe that expressed its potential early and continuously. This does not imply purpose. It implies richness. As scientists continue to analyze Webb's data, they are refining a new narrative of cosmic beginnings, one that emphasizes readiness rather than hesitation, capability rather than fragility, emergence rather than delay. This narrative does not replace the old one entirely, it evolves it. The Big Bang remains the beginning. Expansion remains central. Gravity remains essential. What changes is our sense of timing and intensity. The universe's early chapters are no longer quiet preludes. They are active, formative, and decisive. James Webb has not rewritten cosmic history by contradiction. It has rewritten it by illumination. By revealing what was always there, hidden beyond our reach, it has expanded our sense of what the universe was capable of from the very start. And in doing so, it has shifted our understanding of beginnings themselves. Beginnings are not always tentative. They are not always slow. Sometimes beginnings arrive fully capable, ready to build, ready to organize, ready to become. The early universe, as James Webb is showing us, was one of those beginnings. As this realization settles in, cosmology moves forward with renewed humility and renewed curiosity. The story of the universe is not closing, it is opening wider than ever, and with each new observation we are learning to read its earliest chapters, not as fragile drafts, but as confident expressions of a cosmos that knew how to become complex, almost as soon as it existed. As this clearer picture of the early universe continues to take shape, scientists are beginning to confront a deeper implication of everything James Webb has revealed: the idea that cosmic time may not behave the way our intuition expects. For decades, time in cosmology was treated as a steady ladder. The universe climbed it rung by rung, slowly becoming more structured as billions of years passed. Early on, there simply wasn't enough time for complexity to exist. James Webb is quietly dissolving that assumption. What the telescope reveals is not a universe constrained primarily by time, but a universe constrained by conditions. When the right conditions were present, extraordinary things happened quickly. When conditions changed, growth slowed. Time itself was not the limiting factor, opportunity was. This reframing changes how scientists interpret cosmic age. A galaxy that appears too old for its era may not be violating time at all. It may simply be expressing what gravity, gas, and radiation can accomplish when everything aligns. In this view, the early universe did not rush. It acted efficiently. Efficiency, not haste, becomes the defining trait of the early cosmos. This distinction matters because it helps resolve the emotional tension that sometimes accompanies Webb's discoveries. Early reactions framed certain galaxies as impossible or forbidden, but as researchers look more closely, the impossibility fades. What remains is surprise rooted in outdated expectations. The universe did not cheat, it optimized. There is also growing recognition that our everyday experience of time deeply shapes how we imagine cosmic history. Human systems need long periods to build complexity. Civilizations take centuries. Biological evolution takes millions of years. It feels natural to project this slowness onto the universe. But the universe is not biological, it is physical. And physical systems under extreme conditions can reorganize with astonishing speed. James Webb is forcing cosmology to let go of anthropocentric timing. Another insight emerging from Webb's observations is the role of feedback delay in the early universe. Today, star formation is regulated by powerful feedback mechanisms. Radiation, stellar winds, and supernovae limit how fast galaxies can grow. In the early universe, many of these breaks had not yet fully engaged. The result was a brief window where growth could proceed largely unchecked. This window may explain why early galaxies appear so intense. They were forming stars before feedback systems had time to stabilize. Once those systems became effective, growth slowed and galaxies settled into more familiar patterns. In this sense, the early universe was not breaking rules. It was operating before all the rules were fully enforced. James Webb is capturing evidence of that transition. This insight also helps explain why the universe today appears calmer than it once was. The dramatic construction phase is largely over. What remains is maintenance, evolution, and slow transformation. The most explosive creativity belonged to the universe's youth. This perspective lends a subtle narrative arc to cosmic history without imposing purpose. The universe expressed its full potential early, then gradually constrained itself as structures matured. Another important shift concerns how scientists think about rarity. Before Webb, massive early galaxies were assumed to be extremely rare. Now, they appear common enough to demand explanation. This suggests that rarity itself may be relative to observation. If early massive galaxies were always present, but simply beyond our detection limits, then rarity was an artifact of blindness. James Webb removes that blindness. This realization carries a lesson beyond cosmology. It reminds us that what appears exceptional may simply be unseen. The universe has always been what it is. Our perception of it changes as our tools improve. There is also renewed attention on the relationship between early galaxies and dark matter. Webb's observations are prompting scientists to revisit how dark matter halos formed and merged in the early universe. If dark matter structures assembled rapidly, they would have provided deep gravitational wells for gas to fall into. This would accelerate galaxy formation without requiring exotic physics. James Webb's data appear consistent with this idea. Early dark matter halos may have been denser and more effective than previously modelled. This reinforces the idea that known components interacting efficiently can produce surprising outcomes. Once again, complexity emerges from alignment, not novelty. There is a quiet elegance in how these pieces fit together. Faster halo assembly, efficient gas cooling, delayed feedback, and dense environments all point toward a universe primed for early growth. None of these elements alone explains Webb's findings. Together they form a coherent picture. This coherence matters. It suggests that the rewriting of cosmic history is not chaotic. It is structured. Another consequence of Webb's discoveries is the way they reshape scientific humility. When models are challenged, there is a temptation to defend them. The cosmology community has largely done the opposite. It has responded with curiosity, openness, and careful revision. This response reflects a mature field confident enough to evolve. James Webb is not destabilizing cosmology. It is strengthening it by forcing assumptions into the open. There is also a subtle change in how scientists talk about the unknown. Instead of framing gaps as failures, researchers increasingly frame them as frontiers. Webb has expanded the frontier of early universe studies dramatically. What was once speculation is now observation. This shift transforms abstract debates into concrete research programs. Another layer of significance lies in how Webb's discoveries resonate with broader questions about existence. A universe that organized itself quickly challenges narratives of cosmic indifference. It suggests a cosmos capable of rapid structure without fine-tuning. This does not imply intention or meaning, but it does suggest that complexity is not fragile. It is resilient. That resilience may help explain why the universe remains richly structured billions of years later. James Webb is showing us that the seeds of resilience were planted early. There is also an aesthetic dimension to this moment. Seeing ancient galaxies in such detail evokes a sense of intimacy with deep time. Light that left its source when the universe was young now enters human instruments, carrying information across epochs. This continuity bridges vast scales. It reminds us that the universe is not divided into disconnected eras. It is a continuous unfolding. James Webb allows us to witness that continuity directly. As scientists integrate these insights, they are developing a more nuanced language for cosmic history. Words like early, late, fast, and slow are being used more carefully. Timing is being contextualized within conditions. This linguistic shift reflects deeper conceptual change. The universe did not wait to become interesting, it became interesting as soon as it could. This idea may ultimately become one of James Webb's most enduring contributions. It reframes cosmic beginnings not as a hesitant emergence, but as an assertive expression of physical law. As observations continue, some details will change, timelines will be refined, mechanisms will be clarified. But the central lesson appears robust. The early universe was capable, active, and expressive. James Webb is not revealing a universe that contradicts itself. It is revealing a universe that has always been more capable than our first stories allowed. And as this realization deepens, cosmology becomes less about correcting errors and more about expanding imagination, guided always by evidence. The rewriting of cosmic history, then, is not an erasure, it is an enrichment. It replaces a simple linear story with a richer, more dynamic one. A story in which the universe did not simply endure time until structure emerged. It created structure because the conditions allowed it, and it did so with confidence. James Webb is teaching us to recognize that confidence, and in recognizing it, we are learning to see the universe not as a reluctant system dragged into complexity, but as a reality that embraced complexity almost from the moment it existed. As this evolving understanding settles more deeply into cosmology, scientists are now confronting one of the most subtle shifts James Webb has triggered, a change in how cosmic beginnings are interpreted not as fragile moments, but as stable foundations. For a long time, the earliest phases of the universe were treated as precarious. Slight changes in conditions were thought to dramatically alter outcomes. Structure seemed to depend on fine balances, narrow windows, and delicate timing. James Webb is quietly revealing a different picture. The early universe appears not fragile but resilient. Its capacity to form structure does not depend on precise tuning but on broad, forgiving ranges of physical conditions. Galaxies did not emerge because everything went exactly right. They emerged because many different paths led to similar outcomes. This robustness matters deeply. It suggests that the universe's large-scale structure is not the result of a single lucky trajectory, but of a system with many stable solutions. When matter cooled, gravity acted. When gravity acted, structure followed. The details varied, but the outcome was reliable. James Webb is revealing how wide the margins really were. This realization changes how scientists think about cosmic inevitability. It becomes less meaningful to ask whether galaxies should have formed early, and more meaningful to ask how they could have failed to form at all. Given the density, energy, and physics of the early universe, structure formation may have been the default outcome rather than the exception. This reverses an old intuition. Instead of seeing the early universe as a place where complexity struggled to emerge, it may be more accurate to see it as a place where complexity was almost unavoidable. Once expansion slowed just enough, gravity took over with remarkable efficiency. James Webb is providing direct evidence of this inevitability. There is also a growing appreciation for how scale influenced early outcomes. In the young universe, distances were smaller, interactions were more frequent. Matter did not need to travel far to combine. This proximity amplified every process. Gas collapsed quickly. Stars ignited rapidly. Galaxies assembled before dispersal could slow them down. In this compressed environment, time behaved differently in practical terms. Not because physics changed, but because interactions were accelerated by closeness. The universe was dense with opportunity. James Webb is letting us observe the consequences of that density. This perspective also reframes how scientists interpret cosmic smoothness. The early universe was remarkably uniform on large scales, yet wildly active on small ones. Tiny fluctuations grew quickly. Minor variations became major structures. Uniformity and complexity coexisted. This coexistence is a hallmark of powerful systems. Uniform rules applied everywhere, but local differences produced rich outcomes. James Webb's observations highlight this balance beautifully. Another implication of this robustness is how it affects theories beyond galaxy formation. Early black hole growth, chemical enrichment, and even the thermal history of the universe are being reconsidered. If structure formed earlier and faster, then many downstream processes also began sooner. This compresses cosmic timelines without compressing physics. It also means that the universe may have reached maturity earlier than expected. Not maturity in the sense of calm, but maturity in terms of structural readiness. By the time the universe was a few 100 million years old, it may already have contained the seeds of everything that followed. James Webb is showing us that those seeds were not sparse. There is also a shift occurring in how scientists discuss cosmic surprise. Early reactions to Webb often use dramatic language: impossible, forbidden, unexpected. As understanding deepens, that language is giving way to quieter reflection. The surprise is no longer that these galaxies exist. The surprise is that we ever thought they wouldn't. This shift reflects a deeper alignment between observation and theory. Instead of resisting the data, models are evolving to accommodate them. This evolution is not a retreat. it is progress. James Webb is doing what great instruments always do, forcing theory to grow. Another subtle change lies in how cosmologists communicate uncertainty to the public. Webb's findings have captured imagination, but they also demand careful explanation. The goal is not to suggest that everything we knew was wrong, but to show how understanding deepens over time. This nuance matters. It preserves trust while encouraging curiosity. The story becomes not one of failure, but of refinement. James Webb's discoveries also invite reflection on the nature of cosmic storytelling itself. Humans naturally prefer simple narratives with clear stages and milestones. The universe does not oblige these preferences. Its history is layered, overlapping, and continuous. The early universe was not a clean slate that slowly filled in. It was a dynamic environment where multiple processes unfolded simultaneously. James Webb is revealing that simultaneity. This realization encourages a more holistic approach to cosmic history. Instead of isolating star formation, galaxy growth, and black hole evolution into separate chapters, scientists are increasingly viewing them as intertwined threads. Each thread influenced the others from the very beginning. This interdependence may explain why early structures appear so coherent. They were not assembled piece by piece. They grew together. James Webb's ability to detect these early systems allows scientists to trace those threads backward with increasing confidence. There is also a broader philosophical resonance in this picture. A universe that is robust, capable, and flexible challenges narratives of fragility. It suggests that complexity does not require constant rescue. It emerges naturally when conditions allow. This does not diminish the rarity of life or consciousness. It places them within a context of a universe that is fundamentally creative rather than precarious. James Webb is reminding us that the universe is not barely holding together, it is expressing itself fully. As research continues, this idea of robustness may become central to how cosmology frames its foundational assumptions. Instead of asking how finely tuned the universe must be, scientists may increasingly ask how tolerant it is. James Webb's data suggest high tolerance. This tolerance helps explain why the universe remains structured billions of years later, even as expansion accelerates and matter thins out. The early establishment of structure created enduring frameworks that persist. Those frameworks are still shaping cosmic evolution today. There is also a sense in which Webb's discoveries bring the early universe closer emotionally. It no longer feels like an alien, inaccessible phase. It feels like the energetic childhood of a system we are still part of. The same gravity, the same physics, the same laws apply now as then. What changed were conditions, not principles. James Webb allows us to see those conditions clearly. As cosmologists integrate this perspective, they are rewriting cosmic history not as a correction but as a deepening. The universe did not surprise us by behaving strangely. It surprised us by behaving confidently. This confidence challenges us to rethink what we mean by beginnings. Beginnings are often imagined as tentative. In the universe's case, the beginning was decisive. The early cosmos did not hesitate to build. James Webb has given us the evidence to see that clearly. And as this understanding continues to mature, it reshapes not only how we describe the universe's past, but how we imagine its capacity. A universe that organized itself rapidly once conditions allowed is a universe that takes full advantage of its own rules. In that sense, James Webb is not just revealing ancient galaxies, it is revealing the character of reality itself. A reality that does not wait for permission to become complex. It becomes complex because complexity is what its laws make possible. And from the very beginning, those laws were ready. As this broader picture continues to unfold, the final and perhaps most profound implication of James Webb's discoveries begins to take shape. A re-evaluation of what it means for the universe to be understandable at all. For much of modern science, understanding has meant reduction, breaking complex systems into simpler parts and explaining them step by step. This approach has been extraordinarily successful. It gave us relativity, quantum mechanics, and a workable timeline of cosmic history. But the early universe revealed by James Webb resists simple reduction, not because it is unknowable, but because it is deeply interconnected. Processes overlap, causes and effects blur, multiple mechanisms operate simultaneously, reinforcing one another. The universe's earliest structures did not emerge from a single dominant factor, but from the convergence of many ordinary processes acting together under extraordinary conditions. This convergence challenges the expectation that there must be a single explanation for early complexity. Instead, the universe appears to have been shaped by a network of influences, none of which alone tell the full story. James Webb is teaching cosmology to think in terms of systems rather than sequences. This shift is subtle but transformative. It moves the field away from asking which process came first and toward understanding how processes interacted. Gas cooling, gravity, radiation, turbulence, mergers, and feedback did not take turns. They coexisted. Their interactions amplified outcomes. In such a system, speed is not surprising. When multiple reinforcing processes act together, change accelerates naturally. This perspective helps explain why early galaxies appear so complete. They were not assembled piece by piece. They grew within an environment where everything favored growth at once. James Webb is capturing the imprint of that environment. There is also a deeper lesson here about predictability. In linear systems, prediction is straightforward. In interconnected systems, prediction becomes probabilistic. Early cosmological models leaned heavily on linear intuition. Webb is revealing a universe that behaved more like a complex system from the very beginning. This does not make the universe unpredictable, it makes it rich. Rich systems can produce similar outcomes through different pathways. This explains why early galaxies show both diversity and consistency. They differ in form, size, and activity, yet they all exist far earlier than expected. The universe did not follow one blueprint, it explored many. James Webb's observations validate this exploration. Another important implication concerns the role of simplicity in scientific storytelling. Simplicity is valuable, but it can become misleading if it erases interaction. The early universe was simple in its laws, but not in its behavior. James Webb is forcing cosmology to embrace that distinction. This does not undermine the elegance of physics. On the contrary, it highlights it. Simple laws can generate astonishing complexity when conditions allow. The early universe was a demonstration of that principle at the largest possible scale. There is also a shift in how scientists think about cosmic surprise itself. Surprise is often framed as a failure of prediction. In reality, surprise is a signal that understanding is expanding. James Webb surprises are not warnings, they are invitations. Invitations to widen models, to relax assumptions, to listen more carefully to what the universe is actually doing. This listening requires patience. Webb's data are rich, but interpretation must be slow. Each observation opens multiple explanations. Premature certainty would obscure nuance. The cosmology community has largely embraced this patience. Instead of declaring revolutions, scientists are methodically building a more flexible framework that can accommodate early complexity without abandoning established physics. This measured response is important. It ensures that the rewriting of cosmic history is durable, not reactive. James Webb's influence also extends beyond academic circles. It reshapes how humanity relates to cosmic time. A universe that became complex quickly feels less distant. It suggests that structure, organization, and richness are natural expressions of reality, not rare accidents. This perspective can subtly change how people experience their place in the universe. We are not living in a cosmos that barely tolerates complexity. We are living in one that expressed it eagerly from the start. This does not imply purpose or intention, it implies capacity. James Webb is revealing a universe that fully uses its capacity. There is also an important clarification emerging about what Webb has not done. It has not overturned the Big Bang. It has not invalidated expansion. It has not replaced gravity or dark matter. The foundations remain. What changes is our sense of tempo and confidence. The universe did not tiptoe into structure. It moved decisively once conditions allowed. This decisiveness challenges narratives of cosmic fragility and replaces them with narratives of resilience. This resilience may be one of the most enduring lessons of Webb's mission. As researchers look ahead, they are increasingly aware that Webb's discoveries mark the beginning of a long process. New instruments will build on its findings, new surveys will test its implications. The early universe will remain a central focus for decades, but the conceptual shift has already occurred. Cosmic history is no longer framed as a slow, hesitant climb from simplicity to complexity. It is framed as a rapid flowering followed by long evolution. This flowering does not diminish later cosmic chapters, it contextualizes them. The calm, expansive universe we inhabit today is the descendant of an energetic youth. James Webb allows us to witness that youth directly. There is also a quiet humility that comes with this perspective. It reminds us that our models are always provisional. They reflect the best available evidence at a given moment. When evidence improves, models must evolve. This is not a weakness of science, it is its strength. James Webb is an example of that strength in action. It has not delivered final answers. It has delivered better questions, questions about how quickly structure can form, about how tolerant the universe is to variation, about how interconnected processes shape outcomes, about how much complexity is natural rather than exceptional. These questions will guide cosmology forward. There is also something deeply fitting about the way this story unfolds. Light that left its source more than 13 billion years ago now reshapes human understanding. The universe reveals itself slowly, even when its own processes were fast. This contrast between cosmic speed and human patience defines the scientific journey. James Webb stands at the intersection of those scales. As we integrate its discoveries, the universe appears less mysterious in one sense and more mysterious in another. Less mysterious because we can see more clearly, more mysterious because what we see is richer than expected. This is a productive mystery, one that deepens curiosity rather than closing inquiry. In the end, the rewriting of cosmic history prompted by James Webb is not a dramatic overturning of knowledge. It is a quiet expansion of perspective. The universe did not contradict itself. It exceeded our expectations. And as those expectations continue to adjust, a new story emerges. One of a cosmos that did not wait for billions of years to become interesting but expressed its full creative potential almost as soon as it could. James Webb has given us the evidence to tell that story honestly, a story not of fragility but of strength, not of hesitation but of confidence, not of delay but of readiness. And in telling it, we come closer to understanding not just how the universe began, but what it has always been capable of becoming. As this long journey through James Webb's discoveries gently comes to rest, what remains is not a conclusion in the traditional sense, but a quiet reframing of how the universe is allowed to exist in our minds. The early cosmos, once imagined as a hesitant beginning, now appears as a confident unfolding, not rushed, not forced, but fully capable from the moment conditions allowed expression. What James Webb has revealed is not a universe struggling toward order, but one that recognized opportunity and responded naturally. Complexity did not wait for permission. Structure did not require exceptional circumstances. The universe acted because acting was what its laws made possible. This realization softened something important. For a long time, cosmology carried an unspoken tension, the sense that everything meaningful happened slowly, reluctantly, and against the odds. Webb replaces that tension with calm assurance. The universe did not barely succeed. It functioned exactly as it was able to function. From this perspective, early galaxies are no longer anomalies. They are signatures, evidence of a universe comfortable with its own rules, confident in its capacity to build. There is something deeply grounding in that idea. It suggests that reality is not fragile at its foundation. It does not depend on perfect balance or constant correction. It flows forward, exploring what is possible, settling naturally into structure when conditions allow. James Webb does not tell us that the universe is finished explaining itself. It tells us that explanation itself must remain flexible. Every generation of observers sees the universe differently, not because the universe changes, but because our ability to listen improves. Webb is one such improvement: a quieter ear, a deeper gaze, a longer patience. The ancient light it collects does not shout. It does not demand urgency. It simply arrives carrying information shaped by billions of years of travel, asking to be interpreted slowly, and slow interpretation is exactly what this moment requires. There is no rush to finalize cosmic history. The universe has already lived it. Our task is not to keep up, but to understand, gently, honestly, without forcing neat endings onto a story that was never meant to end. What emerges from this understanding is a universe that feels less distant and less alien, not because it is familiar, but because it is consistent. The same physical principles that governed the first galaxy still govern the quiet motion of stars tonight. Nothing fundamental has changed, only our perspective has widened. James Webb reminds us that knowledge does not arrive as a sudden revelation. It arrives as gradual alignment between expectation and evidence, between imagination and reality. And when alignment happens, the universe does not become smaller, it becomes clearer. As you rest with these ideas, there is no need to hold on to them tightly. Let them drift, let them blur, let them settle where they will. The universe does not require attention to continue existing, and understanding does not require effort to remain meaningful. Long after observation ends, long after questions fade, the universe continues, expanding, evolving, expressing what its laws allow. James Webb has simply given us a chance to witness that expression a little earlier in the story than we ever could before, and in doing so, it leaves us with something calm and enduring, a universe that did not wait to become complex, a universe that did not fear its own potential, a universe that from the very beginning was ready and still is.